Hi, I'm Jan. I'm a blockchain researcher at Quantstamp. And today I am here at Blockgeeks, and I want to talk to you about a topic that I find super interesting and fascinating, but not a topic for which I am necessarily a sort of academic expert. And that's ZK STARKS. So these are zero-knowledge proof systems that can be used to verify integrity of computations while keeping things private and secure. And they're a really cool technology for the upcoming blockchain, space, in the sense that I don't think they've been implemented in a feasible sense just yet, but they will be shortly, and there's lots of academic interest in it. So just to clarify, I've read a lot about this topic, but I'm not a researcher in ZK Stark specifically, and so I may make small mistakes when it comes to terminology or content in other cases, but I'll do my best to minimize this. And I'll also point out that I'm not here to go into a very deep dive for this topic. There's a lot that can be said and a lot that can be read about this topic, but I'm going to just highlight what I think are some really cool sort of mathematical tools to overcome the problems that need to be overcome in order to implement such a system, and not necessarily define every mathematical term, so that this is not a lecture in the mathematical sense. So I won't necessarily prove any theorems, I won't necessarily define every term, but I will mention them so that if you are confused or if you are interested, you can go out into the wild and find the information and hopefully be able to do more than just scratch the surface, because now there's some context surrounding these terms and theorems and other facts. So the last thing I want to mention is most of the material, if not all of the material on these slides, I did not create. I've adapted them from other sources, and they're on the slides so that I'm not stealing them. Because, like I said, I'm not the one coming up with these nice new novel ideas that are super cool. I'm just presenting them because I think they're super interesting and going to be super useful. And they're also really technical. So videos like this, I hope, will help spur interest and also convey what this technology does. Okay, so let's move on. We're motivated this technology with a scenario. And the scenario is somewhat straightforward. It is a little bit contrived, but this is a scenario that's actually used in one of the papers that describe this technology. And it's not too unrealistic. Suppose that we have a high-level politician who's been offered a position. So someone's running, say, for President of the United States or Prime Minister of Canada or whatever they want. And they're offered this position on the condition that they've never committed any serious crimes, right? So if you've committed murder, maybe you're not eligible for this position, and this is certainly not an unreasonable expectation of our politicians. And the politician says, well, I'm perfectly fine, I have not committed any crimes, and if I had committed any crimes, we're going to pretend we're in a perfect society where someone would have caught them and this data would have been tracked. In particular, the unique data that ties this person to that specific bad crime would be recorded somewhere by some authority. And in the real world, this data is typically the DNA. This is pretty indisputable evidence that you were somewhere where something bad happened, where they had to collect DNA. Or some were good in some cases, but primarily some were bad. And so the high-level politician, the presidential candidate or the prime minister candidate or whomever, they want to take this position, and they need to prove that they are not guilty of any such crimes. And so he or she speaks to the authorities, who maintain a massive database of DNA records for criminals or suspected criminals. And if this politician wants to convince the public, the masses, that he is in fact, innocent, or at least not ever convicted guilty of anything, he would need to prove that his DNA is different from every single entry in that database. Because obviously, if he was in the database, that means he was picked up on some crime, charged, or at least suspected. And he doesn't want that, because then he doesn't get the job. And so he wants to prove this. How can we solve this problem? In fact, on the surface, this is not a particularly challenging problem to solve. The naive solution is to just check the entire database. This is, not unreasonable, except that the database might be really large, and it might be very difficult for an individual member of the public to do this, because they don't have the database of the evidence, And even if they had the database, they may not have the computational resources to check that the DNA sample of the candidate is missing from this database, because they would have to check potentially millions of entries, and their MacBook will run out of battery before this happens. And this is kind of annoying, but there's also the issue of then you're exposing this massive database of DNA of suspected or convicted criminals to the public, which might actually be a privacy violation, or at the very least be frowned upon by a lot of people, particularly the people whose DNA is in this database, because they trusted the police to keep this data secret and not public, so that unless someone has reason to check that they are a criminal, they will not check that they are a criminal, right? They will have the benefit of being perceived as an innocent person. So, what's another approach that could be taken? In the real world, what might happen is that you would hire someone that can be trusted, a third party, to perform this check. But this still exposes this precious private data to people for which the people in the database may not want to have access to this information. And in particular, this still requires some level of trust. One problem with the initial check of just making the police run the check is that we might not be able to trust the police. And if we don't trust the police, there's not necessarily any guarantee that we trust this possibly arbitrary third party either, because maybe the police are paying them off, maybe the politician's paying them off. A third party is even less likely to be trusted in many cases. And so this is an option, but it's not the best option. And so ZK-STARKs actually provide a solution to this. And I haven't really told you what a ZK-STARK is. Instead, what I'll try to describe is what we want them to be, and then we'll go about showing how to build one, or at least describing the key components of a ZK-STARK. So ZK-STARKs help in this scenario by providing a method that enables the police to prove that a politician is not in the database. So the police can come up with a certificate, in some sense, that says DNA of politician X or would-be politician X is not in database D. It requires only trust in the police, which unfortunately sort of has to be taken in this scenario, because if we can't trust that the police has a complete record, then it's hard to enforce this mechanic anyways. It does not require the police to reveal any of the data. So they don't need to say, here's my list of candidates. Note that here's my list of convicted, say, felons, and note that the political candidate is not on this list. They can keep all that secret. And what is really nice, and what is actually one of the biggest technical innovations of this solution, is that the proof is smaller than the size of the database. So it's actually sublinear in the size of the database, which means if there's a record somewhere of 1 billion people, the police might only need to provide data that's equivalent to 1 million people, which is really cool. The exact ratios depend on the implementation and the math, and we won't get into the exact complexity of the savings, but it will be smaller than the entire set of data, which is really nice because it's more portable and it's more easily verified. So, what is the ZK-STARK? So a zero knowledge proof, which is sort of the foundation of the ZK-STARK, it's the ZK, the first two letters, is a proof of something that doesn't leak any information about that something. In short, you want to reveal that you know something without telling the party that you're revealing your proof to what that something is. So in a slightly more mathematical sense, we're given a function f and a private input x and some public output y. And the zero knowledge proof would say, prove to me that you know x such that f of x gives me some desired output y, without actually telling me what x is. Because obviously if you tell me what x is, I can compute f on it and I can check whether or not you're lying to me. But the magic here happens in that you keep this private input x all to yourself, which is really kind of nice. In fact, we'll also make it be shorter than what x could be in some cases because of this succinctness property that we're going to have. And this might seem like a contrived definition, but in fact it's not. There are a lot of useful mathematical constructions in the blockchain space and elsewhere for which functions can conform to this type of structure or have these properties. One such function that conforms to this structure is mimic. it's a cryptographic hash function that can be applied in the blockchain setting to solve some interesting use cases. So in particular, mimic can actually be seen as a so-called verifiable delay function, which is a function that is fairly slow to compute, but very quick to check. And so you can take this function, which I won't go over the detail of, but it's nice in this mathematical sense that it's fairly algebraic, and you don't need a lot of like if statements or conditionals. And so coding it is almost purely arithmetic. And that would be helpful for later. But it's this nice mathematical function that you can sort of show that it takes a long time to prove something about if you run it in one direction. But you can actually compute the inverse of this function, and it turns out one of these directions is slow while the other is not. And so if you just switch the arrows on where your inputs and outputs go to this iterative function, one of them is slow, one of them is fast, and that's really cool because you can build things like randomness beacons out of verifiable delay functions. And there are other applications in the blockchain space for functions of this sort, because basically you can take a long time to do some actual work, but then always in the future verify that was always done correctly once you know what the answer could be. And this is super cool. I won't go into the specific applications of mimic or verifiable delay function because I could probably talk for minutes or hours on each of these topics on their own, and that's not what we're here to talk about. But it serves as an example that this f of x sort of definition of what a zero-knowledge proof is actually maps to something kind of useful, which is nice because otherwise this is just a purely theoretical construction, which maybe we don't need to be talking about right now, and we could wait another couple decades. But this one actually could be useful. So hopefully I've conveyed that zero-knowledge STARKS actually have the potential to be very useful very soon. The hard part here is actually the succinctness and not the zero-knowledge. So the zero-knowledge of not revealing what your x is, actually it turns out this has been studied mathematically for quite some time. And there are some nice ways to do this that correspond to some nice classes of problems called NP-complete problems, which I won't get into, but are very well studied in the academic setting and encompass a wide range of useful practical problems in the real world. And so we won't explore many of these constructions, but there are lots of them, and there are really cool ones, some including coloring and hats. And just as a reminder that these are not my materials, throughout there are lots of pointers to some really good materials, and so far everything I've taken has been taken from the paper on ZK-STARKS itself, which is a great resource, but it's awfully technical. There are other less technical resources out there. The one pointed to on the slide is really good for conveying what a zero-knowledge proof is, not necessarily what a ZK-STARK is. That's not to say it's bad, it's just not my favorite. My favorite is the material produced by Vitalik Buterin, who has this 3-part series of blog posts that illustrate how many of the more technical features of ZK-STARKS are actually overcome in math without getting too mathy, but not just saying here's a polynomial that does something, here's the specific polynomial. And so we're going to take that level of detail in these slides because I'm going to use Vitalik's resources. The key ingredients we're going to need to make the system work. We're going to need to encode our problem as a polynomial. I've mentioned polynomials a few times now, probably out of context. This is why. It turns out if we can map our computational programs into a polynomial, the problem becomes somewhat simpler. This does mean non-deterministic computations will be somewhat annoying, and I'm not actually sure there's a technical solution to them, so we'll just ignore them and we'll assume everything's deterministic for now. It's not that unreasonable an assumption. We're going to need random sampling in order to get this sublinear property in our proofs. So instead of showing everyone everything for a proof, right, we want to only show some things, not the secret zero-knowledge stuff, but the certificate will need to be smaller than the size of all the data we're using. And so we need some way to make sure that we take only a small part of it And we should do that randomly so that no one can cheat, unless they're really, really powerful. And I don't think even that's a concern. And then, of course, we want zero knowledge. We want to make sure that we don't leak any information that we don't want leaked, right? And so if we can tackle these three problems, we have a pretty good way to build a ZK-STARK, and that'll become clear as the next slides come on. So the next few sections of the talk, which aren't really broken down into sections, but are concentrated into tackling these three areas. So if some things appear out of context, I apologize. In the end, we're going to try to glue them all together and make it work. So first, encoding a problem as a polynomial. Here's an example of a program that we're going to encode as a polynomial. And here it's a little contrived in the sense that everything is fairly simple. We just want to make sure that after some specific number of steps that our particular variable has a particular value, in this case 42, after 1,000 steps. And here's the sort of easy way to check that this works. Well, if you want to prove that you did this to me, well, I'll just say, give me your VM dump of all your memory for the first 1,000 steps, because if you ran this for 1,000 steps, you should have this data and you should be able to give it to me. And then I'll check that you started where you should have and you ended where you wanted to, and things will be all right. Except that requires a bunch of checks, right? It requires this 1,000 steps, which is not sublinear. It's in fact exactly the amount that was requested to be run in terms of execution size. And we do need to check that from step I to step I plus 1, everything went the way you wanted it to, right? That you didn't perform any weird steps in between and didn't try to cheat or try to skip, and you didn't give me arbitrary values, that every value from one step depended on the value in the previous step, right? And so in this case, we can encode that as a polynomial as well, which is very nice, but in general, this might be a little bit more challenging. And one of the big issues I see with ZK-STARKs, again, maybe this has been overcome, but I'm not necessarily implementing one of these on my day-to-day job, is transforming arbitrary code into such a polynomial. But if we do have one, we'll show how we can make this work. And so, assuming we have a nice polynomial, what we have to do is make sure that you can't cheat by giving me an arbitrary set of 1,000 values. And to do this, we're basically going to just add redundancy and make sure that if you do cheat in one spot, you will cheat in many spots. And so even with a small number of questions for you, you'll be able to, the verifier, us, will be able to check that you did in fact cheat. Because if you cheat somewhere, you'll basically be cheating in some large portion of steps. And so we probably would have found that you cheated. And if we do the math really nice, this turns out to be super efficient. A slightly less explicit example, and one that is less tied to specific instances of code, is the following problem. You want to prove that you have a polynomial p, takes one variable x, such that for the first million values of x that you give it, only integers in this case, that this polynomial only ever comes out with a value that's between 1 and 9 inclusive. So if I give you p evaluated at 367, maybe it comes out to 7. But if I ever give you a value within the first million integers, positive integers, that gives me 10, that's not a 9. And so you shouldn't be able to prove this to me. And that would be cheating. And so you want to prove that you actually have such a polynomial that has this nice property. Because if this polynomial maps to a nice program, maybe one that's a little bit nicer or more useful than the last program, then this is valuable to me in some sense. And so the naive way to do it is, well, just give me the polynomial execution on the first million values of x. This is certainly feasible. Polynomials typically don't take too long to compute, especially if it's a small degree, and you could do this. But now your certificate size is 1 million, and that's less than ideal. We want to do better than that value. We want to do sublinear, and here my constraint is over 1 million values, so I want to do strictly less than 1 million. And so if you give me 999,000 and 999, then I'm probably convinced that you're going to work, that you have polynomial for which this property holds. But maybe that one value I didn't ask for jumps up to 11 or 12 or 600 billion or something that's really not between 1 and 9. which case, I got lucky, or say you got lucky, the person trying to prove it got lucky, but this is still undesirable. So we want to make sure that this scenario doesn't happen, and we want to actually drive the number much closer to, thousands as opposed to hundreds of thousands or less. We want to do as best as we possibly can, so that maybe I only need to ask you 40 numbers, right? If I ask you 40 values of x and they're all within 9, and then I could still be convinced with some nice high degree of probability, and that would be ideal. And we're going to show how this can be achieved in some sense. But I won't do the exact math computations, so we'll just do ideas that show how this could work. And if you're interested in how many specific values you actually need to make, I encourage you to read the papers or read the theorem or ask people who are developing these ideas, because they will have better answers for you than I will. I just think it's super cool. So we can redefine this problem so it's a little bit easier to prove something about. For reasons that will hopefully become clear, we're going to define c of x to be a polynomial such that it's 0 if x is between 1 and 9 and non-zero everywhere else. And this is really easy to do because in order to set a polynomial to be 0, you just need to make sure that the x value that you want to be 0 is one of the roots of the polynomial. And so we can compute one really easily, namely the one that's on the screen. If you let c of x be x minus 1 times x minus 2 times x minus 3, up to x minus 9, then c of x will be 0 only at the values 1, 2, 3, up to 9, which is really cool. This is first-year calculus or high school math, depending on where you're watching this from, maybe. And this is well known. It'll be non-zero everywhere else. We don't know what values it'll take everywhere else, but we know it definitely won't be 0. That's helpful, because now we can restate problem 1. Instead of proving to me that you know p of x, with those other conditions, I can now say, prove to me that you know p of x such that c composed of p of x is equal to 0 for all the values that I care about. And this is nice because I can prove this a little bit more concretely than in the last case. Because if we look back at the last case, there's a lot of English there and a little bit less math. Here we're taking out some of that English and putting in some very formal math, right? Here you just need to prove to me that you have a nice polynomial p that, if you compose with c in this order, comes out to the right value we want. And so this is really nice. But there's still this issue of for x between 1 and 1 million, which is annoyingly not mathy right now. It's mathy, but maybe we can make it more formal so we can prove things using only polynomials. And in fact, we can do this. So keeping in mind our function c and the fact that you want to prove to me that you have some p that stays within this bounded region, I'm going to define this other polynomial, z, where z has zeros everywhere on the first million x values. So z will be 0 on 1, 2, 3, 500,000, all the way up to 1 million. And that might seem arbitrary, but if you know a little bit about polynomial math, then you might recall that there's this theorem that says any polynomial that equals 0 at x for all values in some region must be a multiple of the polynomial that has zeros at that region. And so now I can redefine problem 1 as the next version of it, which is prove to me that you know p of x and d of x such that if you evaluate c on p of x, it had better be equal to z times d for some d. And so now the proof is very mathy in the sense that you only have to give to me 2 polynomials, right? And they just have to satisfy some nice equality. And that's easy enough to check. Easy enough being asterisk, because there's always low-level details that we need to overcome. But the core idea is that now we just need to check the quality of these polynomials. Okay, so if you want to prove to me that you know p of x and d of x, what I'm going to get you to do is compute p of x on way more things than you wanted. Instead of computing p of x on only the first million values of x, I'm going to get you to compute it on the first billion values of x. And then we're going to get you to commit these values to a Merkel tree of the data. So you'll put a billion leaves in your Merkel tree, and then you'll build this Merkel tree where you pick two that are next to each other, hash them, and then put the result of hashing the concatenated hashes together in an internal node. And you'll build this Merkel tree up. This is a fairly straightforward construction and a very popular tool in cryptography. But you'll commit to all these values, because a Merkel tree, once you hash them, once you change any one particular value in these billion executions, the whole tree changes, or at least the root down to that leaf that you change certainly changes. We're going to get all of those values locked in. And now all you need to do is commit to this Merkel tree. You can provide the verifier, the person checking that you did all this work, with the root of this Merkel tree. And now the verifier will say, what was the value you got in this particular leaf that led you to hash to this? And as long as you can always answer these questions very nicely, you are showing the verifier that actually you did all this work, and you did it with the right values of P and D. If you cheated in the first million spots, chances are you cheated somewhere else after this first million to the remaining billion that you had to compute. And the math actually works out very nicely that if you even do somewhere around 16 or 32 queries of this form, you can discover that someone cheated and used the wrong P throughout. And the details of this are a little bit too technical for what I want to aim to convey to you for this talk. But it's actually really cool, because now instead of proving to me with a million checks of the polynomial P, you can do this, in certainly less than a couple hundred, which is really, really cool. And the full details are definitely available on Vitalik's blog, and he goes over the math in significantly more detail. In the interest of time, I'm going to keep going. This is only one piece of the puzzle, after all. We've discovered that we can use polynomials to amplify errors, because we're going to make you do extra work that will sort of betray that you've cheated somewhere else, which is kind of cool. The problem is, all these queries could still put all this data onto some polynomial of the appropriate sort of structure, right? They might map to some P that satisfies some parts of this equation, but not necessarily the right P, right? It's still possible that you've gotten lucky as the prover, and this is problematic. And so what we need to do is discuss how we're actually going to check that you've gotten the right P. And for this, we need to check that you actually develop data that fits the right polynomial P. And for this, in order to do this, we need to check some number of points on this P. And remember, we want to do less than some bound of checks, because we want to be more efficient than just running the computation ourselves. And so this is a problem called low-degree testing, where we want to check that some polynomial is of some appropriate degree, which is the highest exponent on the variable in the polynomial definition. And ideally, we want to do this with less than that degree. Unfortunately, mathematically, this is somewhat impossible. You typically need more than D points to check if the set of data you have is on one specific degree D polynomial. And that's making our job much more difficult, because we want to use less than D. The whole point of succinctness was to say we're going to do less than D, and this is really annoying. So we have to work hard to get over this. And luckily, there's some really smart mathematicians who have done exactly this. What we're going to do, since we're making you do all this extra work anyways, is we're going to define another polynomial that's kind of nice. It has some nice properties that, instead of being a single variable polynomial f of x, we're going to define a new polynomial g of x such that, or g of x comma y, where we're going to take y to be x to the 1000. And this might seem contrived, but it works out. And it should be noted that you can always find such a g of x, which is nice, because if it was difficult to find such a g of x, this approach would not solve our problem. In order to check this polynomial is the appropriate degree, we're going to define another polynomial, g of x comma y, and we'll do it in such a way that if you give me y is equal to x to the 1000, then g of x comma y, which is g of x comma x to the 1000, is actually equal to our original function f of x. And then what we're going to do is get the prover to verify, the prover to compute this billion by billion square of data where you compute g of xy, where x is the column you're in and y is the row you're in, and just populate the square. So this is a lot of work, but you can get them to do this. This is not necessarily an infeasible amount of work just yet. It's definitely not trivial. And then what will happen is on the diagonal, we have values of g of x comma x to the 1000, namely values of f of x. And now what we'll do is we'll ask the verifier to query specific rows and columns. And then as long as each row and each column satisfies some nice key properties, and enough of these queries that we make are still on the diagonal, then we will get assurances that with high probability, the polynomial being run by the prover is the one we want. And this is kind of neat. Basically, the key insight is that you just need the rows and columns to be on significantly smaller polynomials, which you can ask for big certificates for, right? So if you demand that each row and each column, all of the points in that set, whichever set you query, correspond to some degree 1000 polynomial, then all you need to do is check, say, 1010 of these entries on that row or that column, and that's fine because that's significantly less than the million that you were initially trying to do. And so if you can do that cleverly enough in many ways, or in a nice way, then you're still not making too many queries. You'll still be making far less than a million, which is kind of neat. And again, I'll leave the math to Vitalik because he's studied this in greater detail than I have. But it is kind of neat. You may have also noticed that we can improve this system using modular arithmetic. And you may have also noticed that computing polynomials of high degree actually increases the size of the output by a large amount. And if we compute polynomials of high degree where numerical values grow incredibly large, then even if we're asking for only a small number of queries to be answered, the answers we get back might grow really, really large because the polynomials produce numbers that are bigger and bigger. And so the certificate size that we need may not be bounded. In order to fix both of these problems, that is, to optimize the query computations, that square of space, and to make sure that our certificate size bounds are easy to compute and relatively constant, we can use a modular arithmetic, which basically just says we'll take our numbers and we'll always take them as the remainder after dividing by some other nice number. Or another nice number will be probably a large prime. And if you don't recall what modular arithmetic is, you actually probably use it on a day-to-day basis, right? It's typically seen in clocks all the time, especially in places where you don't use a 24-hour clock, because, for example, if you say, meet me 4 hours after 9 o'clock, people typically understand that's to be the following 1 o'clock, because the clock only goes up to 12 hours, right? And so after that, we start counting the remainder after, copies of 12 in that addition. So 9 plus 4 is 13, minus 12, you get 1 left over, meet me at 1. So we can use modular arithmetic to solve the cases of keeping numerical values relatively small and to actually improve the number of things you need to compute in a square, right? So if we use a sufficiently large prime, where the sufficiently large prime has all the nice properties we want, it should be sufficiently large in the sense that it should be more than the initial size of either one of our axes or sides of that square we wanted to compute. And it'd be ideal if dividing by that exponentiation factor we put to the second argument in the g of x equals 0, then we can actually realize that there's only so many values that you need to compute before things start to wrap. And so here what we can do is take this vertical dimension, and now we realize, well, after doing some division, there's only some smaller number of actual unique remainders available, and so we don't need to compute the whole square. We can compute this sort of rectangle. And that's that's super neat. And then you just change how you query columns or rows in the diagonal as appropriate, because now instead of having a diagonal that runs across a perfect square, you have a diagonal that wraps across this sort of elongated rectangle type thing. Vitalik does a really good job of doing this math analysis as well. So I'll leave it to him. And then the final step, for reasons that sort of are not clear because we're not doing a complexity analysis, is to do this recursively, and you actually get incredibly fast algorithms at the end of the day. And that's sort of the last technical detail of low-degree testing, which, again, I won't go into because I think there's a lot of detail that could be said and not a lot of time necessarily for this brief introduction. But hopefully, now if you're concerned about ZK STARKS, we're not done. But if you're concerned, you might, say, oh, how can I improve on low-degree testing, or why does error amplification work, or why do we need that? Because if you take out any one of these pieces, actually the system doesn't work quite as well as it should. But we are still trying to get to the whole end goal of ZK STARKS. So let's go back to our example and see how can we actually solve this using ZK STARKS. So here what we want to do is trust only the police. And what the police will do is they'll come up with a nice polynomial mapping of the check that says, for each one of my entries, is my entry equal to the entry provided by the political candidate? If the answer is yes, then there would be a problem, and they should say yes. And if it's no, well, then they'll just keep going to the next loop, right? Next entry in the database, and they'll check over all of them. And so now all we need to do is trust that the police can find a mapping of this iterative loop to a polynomial. If they can do that, we believe there are ways, because we've seen ways, that we can amplify any errors so that if they do try to cheat at any point, we will catch them with a small number of checks, right? And then they just need to do this as appropriate. And we have to worry about the low-degree testing whenever we're doing verification and things like this. But this is something we just saw, not super problematic. There have been advancements in recent mathematics to make this happen. And then we have a nice solution to this problem. Note that we never have to, as a public, see the DNA evidence of our political candidate. We never actually see the database of this at all, which is really nice. And even if we don't know which values to ask for, because maybe we're naive and I'm not a mathematician, so if I was going to ask you to verify the STARK, I wouldn't know which values to choose. There are ways around this too, which we didn't really talk about, but you can use the root of the Merkel tree that you have to commit to as a prover to indicate sort of a source of randomness that will be used for each party to determine which checks are performed, because you don't know this root ahead of time anyways, which is really cool, because it also means I don't need to trust that the police and the candidate, or the police and myself, or myself and the candidate have exchanged any secret keys. And this is actually the differentiating factor between ZK STARKS and ZK SNARKS, which is another phrase you might have used, where the latter requires a trusted setup in most cases. Of course, the technical intricacies of how much we save are also interesting, right? And so here we have some nice data taken again from the paper that describes the scenario and this implementation of a ZK STARKS system. It's on the top left. All right, so what did the prover and verifier actually have to do in terms of work and effort? We saw that the prover in particular had to compute large squares of information, which is significantly more than the data that would be required to naively just run this execution. But we're hoping that this has a nice trade-off for the verifiers who want to do significantly less work, because we want to just only pass this really small amount of data relative to the total amount of data that is in the problem set to begin with. And so here we'll look at sort of the worst case example of this data that's been accumulated again by the people who developed the ZK STARK. And this is from their paper. And so for a problem that takes about 10 hours of prover execution time, so for the police to work 10 hours of work, they actually have to do an incredibly large amount of total data being written to their own internal disk. So on the left, we have execution time versus number of operations essentially in the code on the x-axis. And on the far right of the screen is the total number of data that they had to write or commit to at some point. And so 66 terabytes is actually a significantly large amount of work, but they're never expected to share all of this information. They only need to share small parts of this. And so the nice part is that if we move to what the verifier needs to do, for something that's roughly the same, right, 2 to the 36, actually a little bit bigger, instead of 10 hours of work, they do 39 milliseconds of work. And instead of 66 terabytes, they do 66 kilobytes, which is incredibly small relative to the amount of work that the prover had to do. And so for blockchains in particular, where data and storing of data and passing of data is a very, limited resource in many ways, you don't want to pass a lot of this around, we may have to ask people to do a lot of work offline, but online, only small amounts of data relative to everything that we need to do is passed along. And it can be computed very efficiently for everyone else who didn't need to run that execution the first time, right? The verifiers, which is really, really cool stuff. So I believe that brings me to the end. Yeah, the recap. We noted that the key ingredient here is encoding a problem as a polynomial. This will make arbitrary compilation of code to polynomials, I think, problematic. Again, not an expert. Maybe there are compilers out there that do this. If there are, actually, please let me know if there is a way to let me know. I'm on Twitter and things like this. I'd be really interested to see where this goes. We showed that random sampling on an appropriate ballooned size data set would actually get us a solution. We didn't do the analysis, but we sort of saw that if we can transform the problem into a nice provable statement where you have to also have constraints hold on many more points, then you only need a small number of checks to make sure that you weren't cheating in the first place. And we showed that we never really need to leak anything at all, right? In the input to any of that data, it was nothing leaked that shouldn't have been leaked. I don't know how to say that more nicely. In fact, I think there's a cryptographic property that's called zero knowledgeness. I think that's a formal definition. So those are the key ingredients. Obviously, I've swept a lot under the rug. This is a lot of technical detail, and I'm, like I said, not necessarily a researcher in this specific area of crypto. So I'm just trying to sort of share with you because it hopefully encourages you guys to, whoever's listening, to read more or be interested. At the very least, it provides me an opportunity to talk at someone and indicate where my shortcomings are so I can go and sort of understand more of what's going on. And hopefully you've enjoyed this without getting overloaded with technical details that were, too technical or too overlooked. So thanks.